This lecture is on the law of conservation of energy. It's called "And Whatever Will Be, Will Be." And there is nothing constant in this world but inconsistency, and that's a famous quote by Jonathan Swift. So, what we want to look at is we want to kind of take everything that we've learned so far and we want to combine it into the term called mechanical energy, and then also apply the law of conservation of energy to a system. There are two equations that are here, and the first one is mechanical energy that we were talking about, and the second one is the law of conservation of energy. So we want to be able to use both formulas in this particular case. Now, this is where the majority of the questions come from. So we've taken a look at all the different types of energy, and we've said, okay, work equals changing kinetic energy. Work equals changing our gravitational potential energy. Work equals elastic energy. Well, if work equals all those things, well, then you can set them equal to each other, and we have the law of conservation of energy. So let's take a look at the first one. It says the total energy. A ball thrown up in the air can have both gravitational potential and kinetic energy. So when you throw it off the ground, it's still moving, therefore it has kinetic energy, and it's still some height above the ground, so it has gravitational potential energy. So whenever you have two of those there, how do we know what the total energy of the system is? So we have to kind of come up with a new term for total energy. And that new term we have is called mechanical energy. It is the sum of the potential and the kinetic energy. Now remember, potential energy could be potential energy due to gravity, or it could be potential energy due to elastic. So it's one of those two terms. It could, in fact, be both. So you have to be able to do this to find what the mechanical energy is. Now, mechanical energy is synonymous with the total energy of a system. Um, in most cases, it doesn't account for things like thermal or electrical potential energy. It's mainly dealing with what we call classical physics or kinematics and dynamics. So if you look at this, it's the sum of the kinetic energy and the potential energy. They're all measured in joules. So when we add them together, you're just going to be adding and subtracting at this point. They are all calculated. They're all calculated in different ways, which we've gone over, and they all have different definitions, but they're all energies. So let's take a look at some of these examples, with the first one being a 2 kilogram spring is compressed and tied such that the spring stores 100 joules of energy. This spring is thrown into the air and is shown to be moving at 10 meters per second when it's 8 meters above the surface of the earth. What is the mechanical energy of the spring? So what I'm trying to solve for is the mechanical energy. Okay. Now it looks like there's kind of a lot of different energies involved here. So we look at our equation. Remember, mechanical energy is equal to kinetic energy plus potential energy. It looks like there's actually two potentials here. You have the energy due to the spring, and then you have the energy due to the position. But also you have the energy of movement. So it looks like we have almost all of our energies here. So we can go ahead and start and take a look at it, and we can say, okay, can I figure out what the kinetic energy is? Can I figure out what the gravitational potential energy is? And can I figure out what the elastic potential energy is? Well, it turns out the elastic potential energy is easy because it actually tells you that. So you know that's 100 joules. The kinetic energy, you're going to have to use the equation 1 half mv squared, which we've covered before. You know that the spring has a mass of 2, so you have 1 half of 2, and then the velocity squared. Velocity is 10. We square it, 1 half of 2 cancels out, and so the kinetic energy ends up having a value of 100 joules. We also need to be able to calculate the gravitational potential energy, which is mgh. Now, the mass is still 2, gravity is always 9.8 on Earth, and the height that tells us in this case is 8. So when you multiply 2 times 9.8, um, 2 times 9.8 times 8, what you end up with is 156.8 joules. So now if we want to figure out what the total energy is, we need to be able to combine all of these individual um, energies together. So we have 100 joules, 100 joules, and 156.8 joules. So the total energy of the system, or the mechanical energy of the system, is 356.8 joules. In the next example, it says you have a 10 kilogram box that has a total of 500 joules. So its mechanical energy is 500 joules. It is stored 4 meters above the surface of the Earth. And it says, how fast is the box moving at this particular point? So I know what I'm trying to do is I'm trying to solve for velocity, which is associated with kinetic energy. Okay, we have this right here. We have the mechanical energy is equal to the potential energy plus the kinetic energy. There is no sort of elastic energy here. There's nothing that indicates it's bouncing or stretching or anything like that. So we can neglect elastic energy for now. So really what we've got is gravitational potential energy and kinetic energy. Or in our case, it would be 500 joules equals mass times gravity times height plus 1/2 mass velocity squared. We have a mass value of 10 kilograms. We have our total potential energy, our mechanical energy, is 500 joules. We also have the height above the surface of the Earth is 4 meters. We do know that it is Earth, so because of that we know gravity is 9.8. So we can go ahead and plug in our numbers now, and we'll get something along the lines of 500 equals 10 times 9.8 times 4 plus 1/2 of 10 v squared. So the first thing that we need to do is we need to solve for this term right here. 10 times 9.8 times 4, and that gives us a value of, when we subtract 500 from 10, or excuse me, when we subtract 500 minus 10 times 9.8 times 4, we end up with a value of 108. So we have 108 equals 1/2 of 10 v squared. Now, 1/2 of 10 is 5, so when I divide both sides by 5, I end up with a value of, that I can go ahead and take the square root of, and you end up with a value of v equals 8.85 meters per second. Okay, this is a lot easier. It seems like it's more difficult, but basically this is the same thing you would do as if you did kinematics to solve for one particular thing and then canceled everything out. It just makes it a lot cleaner. It's all in one particular equation. So if we look at the next example says, what is the mechanical energy of the system given the experimental data below? So what you see here is you have a set of data that has elastic potential, kinetic energy, and gravitational potential. Realize that mechanical energy is the sum of all of these. So you would take 25, 10, and it looks like 4. You would add those together and you would get a value of 39 joules. Because mechanical energy is the sum of both the kinetic and the potential energies of a system. Now to rehash what we started at the very beginning. When we talked about the definition of energy at the very beginning, we said it was the ability to do work. We said it's a conserved quantity. We said that the total amount of energy that you have in a system always has to remain the same. You can change between different forms of energy, but it always has to equal each other. So now what we have is we have similar situations, but now we're going to look very specifically at kinetic energy and potential energy due to gravity, potential energy of elastic and work. You can set any of these two equations equal to each other if the situation warrants it. So for example, if I were to take a ball and take that ball and press it down on the spring, I would be doing work on the spring, and I can set that work equal to the elastic potential energy. If I were then to release the spring, the ball would leave the spring with a certain initial velocity. I could say that the elastic potential energy is equal to the kinetic energy that the ball has at that particular point. Or, halfway up, I could say that the elastic potential energy of the spring is equal to the kinetic energy at that point plus the potential energy that it has due to gravity. And once this ball gets to its highest point and it stops moving, I could say that the elastic potential energy at the bottom is equal to the gravitational potential energy that it has at the top. So depending on the situation, you can set multiple energies equal to each other. For example, if I have the potential energy due to gravity, right before something hits the ground, I can say all that potential energy has been converted into kinetic energy. So at this point, the potential energy at the top equals the kinetic energy at the bottom. So one of the biggest tricks that you have in your tool bag is trying to solve these questions is what two energies can I set equal to each other, and how can I make them cancel each other out? So you see this. This is the law of conservation of energy. This is how it's put on your formula chart. But really, it's easier just to say what two energies can I set equal to each other, or what energy can I set equal to another two energies. It just says the kinetic energy that you have initially is plus the potential energy initially is equal to the kinetic energy final plus the potential energy final. Now remember, this potential energy could be due to elastic or it could be due to gravity. So you need to take that into account whenever you're doing these questions. So you see right here, they're all energies. We've talked about them all before. Initial just means at the beginning. So what is it to start with? Final means what is it when you end with? So in this particular example, it says a roller coaster begins at its highest hill of 100 meters above the surface of the Earth. It says, what is the centripetal acceleration felt by the rider at point A? That point A was missing from the picture. But you want to know what the centripetal acceleration of the rider is at that particular point. Well, that's a kind of a review question. It says centripetal acceleration. Remember, centripetal acceleration requires that you know the velocity and the radius. And the radius is pretty easy to figure out. The radius in this case is going to be 20 meters, which is half the diameter of the loop. So really, the only thing that I need in order to solve this question is I need to know the velocity at point A. What I'm going to do is I'm going to look at it in terms of energy. My assumption is going to say that right here at the top of the roller coaster, the object has a velocity of 0. Okay, because it says it begins, it's starting there. So if it has a velocity of 0, that means it has a kinetic energy of 0. So all the energy at the beginning of this particular situation is going to be in terms of gravitational potential energy. Now, as I go down the roller coaster track, I'm going to hit a bottom point, and then I'm going to come back up. And when I get to this point right here, I have actually two types of energy. I have both gravitational potential energy, but I also have kinetic energy. And what I'm trying to do here is I'm trying to use this relationship of energy to solve for the velocity so I can turn around and solve for the centripetal acceleration. So what I want to do is I want to go ahead and substitute my values in here. So I have mass times gravity times initial height. I have mass times gravity times final height plus 1/2 mass velocity squared. Now, one of the nice things, and this is one of the things that trips people up the most, is they say, but I don't have the mass of the roller coaster. And if you look, the mass is present in every single variable. So it doesn't matter what the mass is, because you can divide by m and it makes no difference. That simplifies our equation just a little bit to the point where we get 9.8 times my initial height was 100 equals 9.8 times 40 plus 1/2 mv squared. So one of the nice things about this is you have these two terms, which are basically, they have the same 9.8 term and then the 140. So you can go ahead and multiply those out and then subtract. And when you do that, you end up getting a value of 588 equals 1/2 velocity squared. So now you would have to go and solve for the velocity. And when you do that, you multiply both sides by 2 to get rid of the half. Take the square root of both sides. And when you do that, you end up with a velocity of something like 34.3 meters per second. Now, a lot of people will make the mistake and say, there's my answer. But remember, we have right here what we were trying to solve for, centripetal acceleration. So we had to go and take this value and plug it in there. So we can now say that our final answer, the centripetal acceleration, is 34.3 squared divided by 20. When you multiply all that out, you end up getting a value of 58.8 meters per second squared. So just to put that in perspective, you would feel approximately 6 times heavier by going this velocity in this particular loop. So it's not very safe, because if you feel 6 times heavier at the top of the loop, it's going to be even worse at the bottom of the loop, and it would actually make it dangerous to the point where people would pass out. So, not a fun roller coaster for you guys to actually ride. The next example says evaluate the validity of the experimental data shown below. And the key to this one is looking at this right here. Remember, mechanical energy is the sum of the kinetic and the potential energies. So when I look at the first data set, I say, okay, mechanical energy is the highest, and that's good. It's 10. And it's the sum of the kinetic, which is 4, and the gravitational potential energy, which is 6. And so that actually makes a lot of sense. This particular set of data is valid. When I look here, though, it says all this energy has been converted to gravitational potential energy, which is 10, and that the mechanical energy is actually dropped. Now remember, mechanical energy is basically what's conserved here. So the mechanical energy should have a value of 10 in order for the law of conservation of energy to be true. So we know this is an invalid set of data. Additionally, remember the mechanical energy is the sum of the kinetic and the potential. You can't take 4 joules and 10 joules and get 6 joules. You can't just add them up and get that. It doesn't work that way. So because of that, there's 2 reasons why this is an invalid data set. The last example we have, it says 100 Newton per meter spring is compressed by a 0.25 meter by 2.25 meters, then released to fire a 0.4 kilogram ball vertically into the air. What is the maximum height the ball will reach? So we have 2 different types of energy here. You have the elastic energy and you have the gravitational potential energy. So what I want to do is I want to say that those 2 things are equal to each other. And the reason why I can do that is at the maximum height, velocity is 0. When the ball is pressed down on the spring, the velocity is 0. So even though there's kinetic energy in between the 2, none of them, the kinetic energy is not relevant for the 2 points that I'm actually looking at. So because of that, I can say potential energy due to gravity equals potential energy elastic. So now you can expand that equation out, and you can say mgh equals 1/2 k x squared. So you have k and x and m, and we're going to assume it's on Earth, so we have g, and we can go ahead and plug in and say 0.4 times 9.8 h equals 1/2 of 100 times 0.25 squared. Now, when you take 1/2 and multiply it by 100 and then by 0.25 squared, and you set it equal to 0.4 times 9.8, you can actually go ahead and divide both sides by 0.4 times 9.8, and you can do this all at once. And when you do, you get a value of approximately, the height is 0.797 meters. Now make sure that you take into account that's a 0.4 kilogram ball. It didn't show up quite so well on some of those printouts, so make sure that you know it's a 0.4 kilogram ball.